Visible to you? Please let me know when my screen is visible to you.
It's visible, ma'am.
Ma'am, it's visible.
Okay, today we are going to start with a discussion on the instruction formats first of all. So this is in continuation with what we have seen in chapter number 5. If you remember, we've already seen certain types of instructions. Okay, typically an instruction format is defined wherein there we specify an opcode, okay, an address field that designates a memory address. Abhi tak we've done the instructions wherein the address generally designates a memory address. It could also refer to a register, however, which we will see in this section now. Okay, so we are going to look at, we've up till now we've seen two addressing modes, if you remember, addressing mode, the direct addressing mode and the indirect addressing mode, right? We will also look at many other addressing modes now in the next section, that is 8.5. Okay, after we have a look at instruction formats. Okay, so the third field in the instruction was a mode bit, right? Now the instructions could be, of different lengths. Okay, depending upon the, if we have so far restricted ourselves to a single address, right? So the instructions that we had generally were limited to a single length. Okay, but if I had a provision for storing multiple memory addresses, for example, then the instruction length would increase considerably. Is that right? Yes. Yes or no, students?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Right. So we may have different lengths of instructions if we support variable number of addresses in our instruction. Okay. Now, accordingly, uh, the CPU organizations, they use different kinds of registers to carry out our instructions. Okay. For example, we have already seen the single accumulator organization. In the single accumulator organization, the accumulator is assumed for most of the operations. Okay. For example, if you remember, we have talked about the instructions such as CLA, CLE, CMA. So all these they largely rely on a single accumulator register to carry out the arithmetic as well as the logical operations. Okay. Now there is another organization called General Register Organization, wherein apart from the accumulator, we use many other registers. Okay, so we may be using two registers or three registers typically. Okay, and accordingly, These organizations are termed as two address or three address instructions. Okay, so uh, mm, mm, if I am able to specify two register addresses or two memory addresses in a field, then I will be using a two address instruction, things like this. Okay, and then the third one is a stack organization. What do we mean by a stack organization? Stack organization means that we are using a stack to implement our operations. So, if you remember, I told you about the stack yesterday and I explained what is a stack. And I told you that one of the uses of stack is to store the return addresses, right? Now, today we are looking at another use of stack. This time it is to help in the execution of the arithmetic and the logical operations. Okay, so we are going to see, based upon these three kinds of CPU organizations, okay, based upon these three basic kinds of CPU organizations, we are going to look at different formats of the instructions. The first one is, we see, a one address instruction. Okay, now these are the instructions that typically use the they typically use AC very heavily. So for example, now how do these instructions, oh I'm so sorry. Does did huh, I'll just have to just give me a minute to navigate back to the same page. So we see, if we had to execute, if we had to write down a program to evaluate this instruction, okay, then how would we do that? Okay, using one address instructions, that means using the accumulator. So um, let me share, I'm just going to copy this expression and do this before you. Why are you joining so late, Nikita? Okay, so this is one address organization or single accumulator organization. Okay. Now, if I have this program is equal to A into B plus, I think this was A plus B, whatever it is, doesn't matter. Okay, C plus B. Please see, these type of questions are very important from the point of view of your examinations. So you get questions like this in your examination, wherein you are asked to, uh, write down a program for execution of this expression, let's say, using one address instructions or two address instructions or three address instructions. Okay, so please see this very, very carefully. Okay, this is very important. Okay, one of the very important topics. So using one address instructions, we are looking at it first. So what do we do? If you remember, we already do this kind of a thing. We simply say LDA AC. If you remember that, LDA A, right? So what will this do? This will simply put into the accumulator the value of A, right? Now, to use the general terms, I'm doing it. I'm just converting it into a general instruction. Okay. So I'm changing it to load A, means the same thing, that A goes to AC, right? Then what do I say? I simply say add B. Okay. What this means is that A and B are added. Basically, B is added to AC, which already has the value of A. So this is now complete. This is now complete. Okay. Now let us store this value in a temporary variable. Okay. So for that, let me say, generally we use STAX or T for temporary variable. So let me say store T. Okay. This will do what? This will, now T may be a memory variable or a register. Okay, I'll say store T, and then I'll say now we can do the same thing for the C plus D, right? So let me just do this here. I'll just simply say C here. C gets transferred, and then I'll say D here. D gets added into AC, and then, right, and then what will I do? I will simply say multiply with T. Okay, so what happens is that AC gets the value of AC into T, right? And then store the result in X. Store the result in X. So what happens then? So X gets the value of AC. Is this okay? Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right. So if these are actually memory variables, then we can just give me a second. So then what we can do is we can simply say in the comments we can show that this is M of A. Okay. Similarly, M of B. Okay. Right? Is this clear? Right. And M of C and M of T, and so you can see this here. Is this clear now to everybody?
Yes, ma'am.
Right. Now let us see if we rather had two address instructions, then how would we have done this? Changing my screen. So on your screen now, we are trying to uh, take up the same expression so that the difference is clear to you now. So when I say two address instructions, means my instruction can handle two addresses. One may be of a register, one may be of a memory, or both may be from memory addresses, or both may be register addresses, right? And this is generally the type of format which is typically used in most of the commercial computers. So what can I do first? See, what I can do is I can first transfer this A into R1. Okay, then add B to R1. You see this here, first two lines, yes or no?
Yes, ma'am.
Right, and then the add thing, right? And then after that, I since I can use another register now. I am not limited only to the accumulator. So this time I don't need to store this A plus B. into a temporary variable, I can in a separate register sum up C plus D. So I'll move C to R2 and then add D to R2. Okay. And then in both the registers R1 and R2, I have these partial sums, partial sum 1 and partial sum 2. Now we can simply multiply R1 and R2. Okay, so that we have the result, let's say in R1, whatever is the first register is treated as the destination. And then we move R1, which has the result to the X, because it has to be, the result has to be stored in X. So any problem in this? This is very simple.
No, ma'am.
Okay. There is no problem or it is not simple.
And this R1 and
Problem.
R2 are AC registers.
These are registers, yes. So
Okay.
two address instructions are they fall under general register organization. So first we saw the single accumulator register organization, in which we saw the that we had to do the entire program using the accumulator only. Okay. Now we are talking about the general register organization. Under this, I will be talking about two address instructions and three address instructions under the general register organization. Is this clear? Right? After this, I will talk about the stack organization. Okay. So we have just seen when I could employ two registers, then or two addresses, then how could I, perform the same functions. Okay, now let us look at the three address instructions. So here you can see that I am using three addresses. So in the first instruction itself, I can say add A1, add A, B, and put them in R1. So this happens that the operand from memory location A is added to the operand from memory location B, and the result is put in register R1. So we are able to, that is because we are able to handle three addresses now in a single instruction. Okay. Similarly, this can be done. So we add C and D and put the sum in R2, right? And then what we do is we multiply R1 and R2 and put it into X. Any problem? Very simple. Yes or no?
Yes, ma'am.
Right.
Yes, ma'am.
So what is the advantage of the three address format? That means actually as we keep on increasing the number of addresses that our instruction can support, the program starts becoming easier to understand, easier to write, yes, and smaller. Okay. But what is the disadvantage? The disadvantage is that the instructions will start becoming very, very, very long. Okay, so you remember that the memory address occupied the major portion in the memory address instructions. You remember that? 12 bits out of
Yes,
the
ma'am.
15 out of the 15 bit, right? For one address. Now if we increase that, then we will substantially increase the instruction length. Okay, so these are the trade-offs between using smaller instructions and bigger instructions, right? Each has its own advantage and disadvantage. Now, stack organization. Now, what happens in stack organization is we see in the stack organization, the instructions are also sometimes known as the zero address instructions. Okay, why? Because we don't need to specify any address. All the operands and their intermediate results are stored on the stack itself. And where on the stack? If you remember, I told you always on the top of the stack, right? So we don't need to have so many registers or variables. We just need to keep track of the only one location in the stack. We just need to keep that means the address of only the topmost element of the stack, which is called as the stack pointer. Okay, so whatever, if I say push, push means adding something to the stack. Pop means taking out something from the stack, right? So push means automatically a new element is added on top of the stack. Pop means automatically the element on the top of the stack is given back to me. Okay, and if I say add, then automatically two topmost elements from the stack are popped, they are added, and the result is put on back to the top of the stack. Okay, isn't this amazing? Right? We don't have to, deal with so many addresses. Okay, so that is why these instructions are also called zero address instructions. So you may be asked to write down a program using a zero address instruction or using a stack. So this is what you have to do. I'll just go over the program with you. So we are looking at the same program now, the same program, please see. Okay, x is equal to a plus b into c plus d. So first of all, what should I do? I will put a into the stack. Okay, for that I say push a. When I say this, what happens? A goes to the top of the stack. TOS stands for the top of the stack. Okay, so a goes on the top of the stack. Then push b, right? Then I'll simply say add. Please see, no address is required now. So I'm simply saying add. It becomes a zero address instruction. So add, automatically A and B are popped from the stack and they are added, and their result is also stored back on the top of the stack. Okay. Then we do the similar thing with C plus D here in the next three instructions. And then what do I say? I simply say multiply. As soon as I say multiply, then in the stack, please see what has happened up till now. If this is my stack, then here on the top of the stack, I already have a plus b stored, right? Right? I already have a plus b. I had stored that. Then over on the top of that, there is already c plus d, right? We did that later. Okay, so this is the top of the stack right now. Now when I say multiply, what happens is that this is popped out and this is also popped out. Both of them are popped out and then they are multiplied. Okay, and result, whatever is their result, it will be stored into, so whatever is the result, this will be stored back on the top of the stack. Okay. So as soon as I say pop, then I will get this result. Is this clear? End of the expression, only the final result will be available on the top of the stack. Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
So how do you have to write your programs? So please practice one address, two address, three address instructions, and especially, okay, and also write down the comments. Also remember to write down the comments. Okay, these comments they are very important. They will fetch you marks. Okay, so if you skip some comment, then your marks will be deducted. Okay. Now I want to do another very important topic with you today, and that is addressing modes. Okay. So, as I told you, these comments are also very important. Okay. So, you should typically take up more expressions and using each of these address instructions, you should try practicing them. Okay. From today itself, you should do this. Okay. Now, let us look at the next topic, that is addressing mode. Now, why do we first of all use addressing modes at all? So, the first thing is that uh, the addressing modes allow a programmer to use a lot of concepts such as pointers, or see the things that you already see are there in your high level languages, such as counters or for loops or while loops. So in assembly language or machine language we don't have all these things, right? So if there is a low level programmer, which initially there were only low level programmers, right? So if there is a low level programmer and he has to write down a program in a level language, then he obviously needs constructs to loop, right? To use things like if then else, to use pointers, right? So for these things, uh, addressing modes help. How, I will just you know tell you. And sometimes we will see, and I'll let you know where, we also use addressing modes to reduce the instruction size. Okay, so how is that done? I will go over that with you. Okay, let us start with the addressing modes. So the first addressing mode that we are going to discuss today is the implied mode. Okay, now in the implied mode, as the name suggests, the operand is not required to be specified. Okay, we neither do we specify the operand nor do we specify its address. The operand is automatically implied. Okay, for example, if I say CMA, what happens? Accumulator is complemented and the operation is complete. We don't need to give any explicit reference to a operand or the operand itself. Similarly, CME, CLA, CLE, CPA, I'm sorry, SPS, that is skip if positive AC, circular write. In fact, all the register reference instructions that are done using accumulator are automatically in the implied mode. You remember I told you what is the speciality of accumulator vis-a-vis a data register or a temporary register? That in most of the operations it is already automatically implied. Now you can see that. Yes or no? Is this clear to you?
Yes,
Yes,
ma'am.
Okay. So again, another example is the zero address instructions in the stack that we have just seen. So when I said push, sorry, I'm sorry, not push, because in push we have to obviously give the element which we need to push, right? But other instructions such as a add instruction or a subtract instruction or multiply, we just now saw, right? They were zero address instructions. Zero address means we did not have to specify the operand. There what was implied? Accumulator was not implied, but top of the stack was implied, right? So again, an example of the implied mode. Now immediate mode means, so if I have an instruction, then in place of the address field we have the operand itself. Okay, so the rest of the fields remain the same. That is, there is a opcode, there is a mode, bit. Okay, and then instead of the address, the operand itself is present in the instruction. Okay, I'll do the example. I'll again go over these modes with the help of a numerical example. Okay, after I explain them. Now, the next mode is the register mode. Okay. Now, after this immediate mode, we already know two modes, that is the direct and the indirect, that we already remember from chapter 5. Yes. And after that, I am going to discuss the register mode. Okay. Now, what is register mode? In the register mode, please see the instruction specifies a register. It instead of a memory address, this field that you see here, this is not required to specify a memory address, but instead the number of a register. For example, if I have multiple registers, let's say R1, R2, R3, R4, then the number of the register which will contain the operand is specified. So that is the register mode. Simple. Any problem? Any problem, students? Please give me the feedback so that I can move ahead.
No, ma'am.
Okay. Now, next mode is register indirect mode. Okay. Now, what happens here is in this kind of a mode, the address part tells me about a register. Let's say it is 1. That means R1. Okay. So when I go to R1, I don't get the operand, but I get its effective address. Okay. So I am getting this effective address 206, memory address 206. When I go to this memory address 206, I will find the operand. Okay. So in register mode, sometimes also known as register direct mode, this one, in this mode, the instruction contained the number of the register in which the operand itself is located. And now in the register indirect mode, we have the instruction specifies the register which does not hold the operand but its effective memory address. Okay, and that is why the name indirect. Okay. Now let us just first make our discussion concrete by looking at some examples. So, so let this be a snapshot of the main memory that we are talking about. Okay, this one. And these are the values of some registers which are given to me. Okay. Now, if my mode is first of all direct address, okay, direct address, please see what is the value of. First of all, you should always locate whenever you given such a question. You should always locate which is the instruction which is being executed right now. Can you tell me which instruction is being executed? Obviously, the instruction whose address is in the program counter. Yes or no?
Yes, ma'am.
So, when PC is 200, I come to location 200 and I start executing this instruction. And what is the value of PC? The value of PC becomes now 20.
One.
It should become 201. But in this case, we are assuming there is a assumption. It is written in your textbook, okay, for this program. And if you get a question like this in your theory exam, and if there is such an assumption, it will be explicitly written. What is the assumption? The assumption is that two words are being used to store one instruction. Now, up till now, if you remember, we only had one word per instruction. Yes, that means, in other words, the length of the instruction was equal to the word length of the computer. But now we are using two words to store one instruction. The first thing is that this may be possible, okay, if the word length is small and the length of instruction is bigger. And now, especially after you have looked at so many kinds of formats, now you know that the instructions could be there could be varying length of instructions. So some instructions may be larger. Okay, so the textbook says that one instruction is being stored in two words. So you can see two words here being used to store the same instruction. So the next instruction starts at 202. So PC will not be incremented by 1 in this case, it will be incremented by 2. So as soon as I fetch my first instruction, PC will be incremented by 2. Okay, that is the first very important thing to be noted. As soon as you get a question like this is the first thing that you should establish. Now, if the addressing mode was direct addressing mode, okay, then let us find out what will be the effective address and what will be the contents of the AC. Okay, so if the mode suggests that the addressing mode is direct, then as we have just discussed, this 500 does not denote a address, it will denote the actual operand. Okay, so what will be the operand in this case? The operand in this case would be, oh, I'm sorry, I'm talking about the immediate mode, not the direct mode. Okay, so in the if the mode is immediate, I'm sorry, so I'm talking about the second operand, the second mode. So if we are talking about the immediate mode, that means the operand is immediately available in the instruction itself. So this 500 is what? This 500 is the, you can see, this is the operand. Okay. And what is the effective address in this case? Well, the effective address is always the address where the operand is stored. Yes? Yes or no, students?
Yes, ma'am.
So the effective address in this case will be, speak up,
500.
beta effective address. Where is this
200.
stored?
201.
At location 201. So the effective address in this case is 201. Any problem? Any problem?
Ma'am, please explain this again.
Beta, what is the immediate addressing mode I've just told you about? Immediate addressing mode means that the address field contains the operand only. Okay. Instead of the address, it contains the operand itself. Okay. So what will be the operand here? Operand will be 500. And what is the address at which it is stored? 201. So the effective address will be 201. Is this clear to everybody now?
Yes, ma'am. Okay.
Yes, ma'am.
Now we are going to look at the direct and the indirect addresses as we did them in the chapter number 5. Okay. So now you should tell me what, so what will be the effective address if the mode is direct address? Who will tell me? Don't look at the screen. Don't look here and just tell me from the snapshot. Nobody knows. Beta, what are you doing? Are you not studying? कितने दिन में पेपर है? पेपर कितने दिन में है? टेस्ट रख दूं क्या तुम्हारा? ये कोई भूलने वाली चीज थोड़ी है बेटा, इतनी इम्पोर्टेंट चीज है। अब आप प्रैक्टिकल भी कर रहे हो, सब आप यही चैप्टर पे बेस्ड प्रैक्टिकल भी कर रहे हो, ये भूलने वाली चीज है। It is very easy for me, please see, not to stop here and just explain and finish my job. But I don't treat this as my job. Okay. I think I have always taken time to make you understand every little detail and understand back if you have had any problems. But then, what do you do in return? Tell me, what can you do in return? Am I audible? Hello?
Yes, ma'am, you're on.
Yes, ma'am.
Somebody there? Can I hear some voices, please? Feels as if
Yes,
I'm
ma'am.
speaking to myself.
Yes,
Yes,
ma'am.
ma'am.
Yeah. So, what will you do in return? Tell me.
Self study.
I can't hear you.
Self study.
Beta, it is high time now. Start studying, please. Okay. It is high time. Start studying. Okay. Only maybe 2 weeks, 2.5 weeks to your exams. Please read the book thoroughly. Go over my lectures. I've sent you all the recordings. Please go over the recordings. First, go over the recordings and then read the textbook. It will be easier for you. Okay? But
Okay.
please start covering up your course now. You will not be. Computer system architecture is a. I hope you have liked the subject, but it is a very different kind of a subject. Okay, so you will not be able to mug it up. That is why I pay special attention to make you understand the concepts so that you don't have to mug up everything. Okay, if it's there in your mind, you don't have to mug it up the last day, and the thing and the thing becomes very interesting for you. Yes or no?
Yes,
Yes,
ma'am.
students, right?
Yes, ma'am.
Okay. So if the mode is a direct mode, then what happens? Then this address is the effective address. We go to this address and what we get is our operand. Okay. So the effective address in this case is, please speak up.
500.
See, I'll
500.
stop the class, I'll stop the class and I'll go. If you don't speak up, I'll stop the class and I'll go. There is no point. I'll record the lecture and I'll send it to you. Okay, what is the point in having an interactive class? I don't need to speak so much for a non-interactive class. I'll just, speak out the facts and I'll be done with. So you can decide what kind of a class you want to have. I'm just telling you now. I'm telling you, you have to at least listen to what I'm telling you. Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes,
Please
ma'am.
give me responses. Please give me responses. I want to feel that this is an interactive class.
Yes, ma'am.
Thank you. Just hold on for a second, please. Yeah, tell me now. I'll start taking names and I'll start asking you if you don't respond otherwise. Okay? So, in the direct addressing mode, the effective address is
500.
500.
yes. And when I
500.
go to 500, I get 800,
Eight
800.
hundred.
which is my operand, and which will be stored in the cumulative. Yes or no?
Yes.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes. Now let's go over to the third addressing mode, that is the indirect addressing mode. Again, that something that we have done in chapter number 5. Okay. So this address tells me the address of the effective address, right? Is that right?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
So when I go to 500, I
Yes,
get
ma'am.
800. 800 this time is the
Effective address.
effective
Effective
address.
address.
Very good. And what will
Effective
be the
address.
operand?
300 is the
Yes, I go again to address 800, and what I find here, that is 300, will be my operand. Is this clear? Right?
Yes, ma'am.
Please sit today
Yes,
itself in
ma'am.
the evening, make some time to practice all these addressing modes today itself. Okay, so 800 and 300. Now we talk about the register mode. Okay, so in the register mode, uh, there will be some register number here, or if you are given a particular register, for example, let's say R1, they have assumed that R1 is the register where the operand is stored. Okay, so obviously there is no memory address here which can serve as the effective address, because the name of the, or in fact the number of the register serves as the effective address, right? So this is being left blank. Okay, you can also, in bracket you can say not applicable, and in bracket you can put in register R1. Okay, for the effective address. Then what will be the operand? Operand is 400. Simple.
Yes,
Any
ma'am.
problem?
No, ma'am.
No, ma'am.
Next, register indirect mode. Now in register indirect mode, so R1 is specified here. I go to R1, I get 400, but this 400 this time is not the operand but the
Effective address.
Effective
effective
address.
address. Yes. So I go to 400 and I get 700 as my operand. So you can see that 400 is the effective address and 700 is the operand. Okay. Now I'm going to do two other modes with you, auto increment and auto decrement. Auto decrement are just like register indirect mode. The only difference is that in the auto increment mode, before we go to this address to get our operand, okay, this address is automatically incremented. Okay, so it will be incremented to, incrementation means always adding of one, right? So it will the value of R1 will automatically change to 401 if I'm employing this auto increment mode. 400 will become 401. I will go to 401. Oh, I'm sorry. I'm sorry. I'm so sorry. I'm sorry. Let me go over this again. So auto increment and auto decrement, as I just told you, are like register indirect, except that in auto increment, the address is incremented, but after we access the operand. Okay, so we go to, as we did in the register indirect, we go to 400. 400, we get the operand 700. We are complete with our task. But after that, after completing this task, that after getting 700, then I increment 400 to 401. So if after the execution of this instruction, you look at the value of the R1, it will become 401. Okay, it is not written anywhere here, but it will become 400. Auto decrement before we access the effective address, before I go to address 400, it is decremented by 1. That means I will go at the address 399 and I will get the operand from there. Okay, now why are these auto increment auto decrement modes supported? What is their advantage? The advantage of auto increment, auto decrement modes is just that, please see, you've done arrays, right? What are arrays? Arrays are all contiguous memory locations. So we access this location, let's say A0, then A1 will be here, then A2 will be here, A3 will be here. Yes or no? Right?
Yes, ma'am.
Yes,
So
ma'am.
every time, what do you have to do? You have to increment your location by 1. If you are going from 0 to n, right? So
Yes,
auto
ma'am.
increment mode is you can be used there. And if we are coming from n down to 0, then the auto decrement mode can be used. Okay, so I go and I access the n minus 1th location, and then I decrement. Each time I decrement and then I access, decrement and then I access. Okay, is this clear? So these are special modes which are used to access continuous locations. Okay, so that two operations are there, is no need for an explicit another instruction later to increment or decrement the register's value. Okay, now we are going to look at 3 modes. Here only 2 are listed, relative and indexed. I will be doing one more with you. So the first addressing mode that I'm going to discuss is the relative addressing mode. Now, in the relative addressing mode, the effective address is found out by adding the value of the address field to the PC. Okay, so if this is my address field and the value of PC is now 202, then the effective address will become 702. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay, and what will be my operand? Let's go to 702. So the operand is 325. Okay. Now the question is, why do we use this relative addressing mode? These are very important addressing modes again, relative, indexed, and then base addressing mode. Why do we use relative addressing mode? Please see, sometimes we need to branch to some other location. Okay, if so for example, we need to go to the starting of a subroutine. Okay, so one way is to employ a BSA kind of a instruction or a one kind of a instruction, जैसी भी आपकी requirement, as per your requirement. Another way is to have a special addressing mode reserved for this. So if we reserve a addressing mode for this, automatically the address field is added to the PC, and what happens when we add something to the PC? We skip those many instructions. Yes or no? Right? And we get a new effective address. Is this clear? Right?
Yes, ma'am.
So relative addressing mode is generally used for program relocation. It is used for program relocation. That means when we want to relocate to some other part of, we want to jump to or branch to some other part of the program. Now let us look at the indexed addressing mode. Now in the indexed addressing mode, the only change is that instead of the PC, I have put in a register called IR. IR stands for the index register. Now you should always remember these registers. Okay, these are very important registers. What is the index register? So as I was telling you about the arrays, right? What happens in arrays? You have a base address. Let's say we put that address in the address field. Okay, so your base address is where your array starts from. So suppose your array is starting from a address 200. Okay, then the first element is stored at address 200 plus 0. Yes or no?
Yes, ma'am.
Yes, ma'am.
Right?
Yes,
So if this index register holds the value of I, you can think, okay, AI. So the base address comes here and the value of I comes here. Okay, so the first address is, let's say, 200 plus 0. I get the effective address of the first element. Then I just need to change the increment the value of IR. The base address remains the same. So this becomes 1. 200 plus 1, 201 is the next element. Then 2, I change the index to 200 plus 2 is equal to 202. I am able to refer to the third element. Okay. So this is called the indexed addressing mode. Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
So let us look at the example. Now, index register is sometimes also referred to as, either it will be referred to as IR or it will be referred to as XR. So the value of XR is given, index register is given to be 100 here. Okay. So what will I do? I will add this to 500. I get what? I get 600 as the effective address. Is that okay?
Yes, ma'am.
600 as the effective address. When I go to 600, I get 900 as the operand. Is this clear to everybody?
Yes, ma'am.
Right? Now,
Yes.
in the base register, the only thing is that we use a base register instead of the index register or the program counter. Now, what happens here is that in the index register addressing mode, the address field had the base address and the index was changing when we changed the IR. But here in the base addressing mode, the base register holds the starting address and the value of the address field will change. Okay, but in any case, one given instant of time, you just have to add the value of base register to the address field to get your effective address. So the mechanism is the same. You just have to add the value of this register to the address field to get the effective address. Okay. Now, this is about the
Excuse me, ma'am.
addressing modes. And
Excuse me, ma'am.
yes,
Ma'am, are you still on slide number 4?
are you still on slide number 4? Didn't you see what slide is visible to you now?
Ma'am, fifth slide is visible right now.
Fifth is visible now. So you
Yes,
saw
ma'am.
all these slides now.
No, ma'am, not earlier. Now that you're scrolling, I can see. Only the fourth was visible.
बेटा ये पहले you should speak up earlier ना, then you should speak up earlier.
मैम
Okay.
पहले समझ नहीं आया था कि उसी स्लाइड से चल रहा है किसी और स्लाइड से.
Okay, can you see now?
Yes, slide number
Yes,
5
ma'am.
is visible.
Okay, so relative addressing mode, we add address field to the PC, right? Then index register mode, address field is added to the instruction register, also sometimes referred to as XR. Okay, and then base addressing mode, address field is added to the BR. So the mechanism is the same. Is this clear?
Yes, ma'am.
Right? Okay.
Yes,
Yes,
ma'am.
ma'am.
Okay.
Yes, ma'am.
So there is a very small topic that I want to do with you next. Maybe just 2 3 minutes, 2 minutes maybe. And then we will finish off this chapter. You should practice these kind of questions. These are very, very important questions. Can you see the screen?
Yes,
Yes,
ma'am.
ma'am.
This kind of example that I did with you today, this kind of example, okay, is very, very important. They are very important. So, direct question is asked, you may be asked for the effective address or the value of the operand or the content of the AC. Now, indirect question, if it is framed, then they may give you the value of the operand and they may ask you the effective address, or they may ask you that please look at this memory snapshot Okay. And now if the operand is 800, which addressing mode is being used? You tell me. So operand is 800, the address is 500. I go back here, 500 is listed here. Which addressing mode? Direct. Okay.
Yes, ma'am.
If the operand is 500, then immediate, right? If the operand is 300, then indirect.
Indirect.
Okay. So you should also do it the reverse way, right? You should find more questions like this, and I'll I was waiting for this topic to finish, so that I can put a question like this in your assignment, because it is very important that you practice these things. So I will be sending you your assignment most probably by tomorrow, and you will have 4 to 5 days to submit the assignment. This will be the second marked assignment, whose marks will be included in your internal assessment. Okay.
Okay, ma'am.
Okay, ma'am.
And uh, please complete your practicals. That means all that I have given. Okay. So that means the register reference and the memory reference instructions, all of them, by maximum this weekend. There are 1 or 2 assembly language programs that I will be doing with you. Okay. Maybe this week, uh, or next week. Okay. So the next thing that we need to see is reduced instruction set versus a complex instruction set, also known as Risc and CISC. Okay. Now what are these? Please see. First of all, we will talk about CISC. CISC stands for Complex Instruction Set Computer. Okay. Now, in this kind of a computer, there were a very large number of instructions. Okay. There were typically 100 to 250 instructions. So for every small uh, operation that needed to be done, there was a new instruction which was added. Okay. So you can see that some instructions that perform specialized tasks are used infrequently, but still they were added to the instruction set. Okay. And at the same time, a very large number of addressing modes were also put in. Okay. And obviously, we have seen that when there are a very large number of addressing modes and we support so many addresses, then the instruction format become variable length. That means some instructions become small, some instructions become uh, longer. So it is difficult to handle such instructions. Okay. So all in all, please see what happened was that when all these things were being done to the instruction sets, the focus was to give maximum benefit to the programmer, that any smallest kind of instruction that he may have to do, there is already a added basic underlying instruction to support that for for any operation that he wants to do. But what was the downside of this? The downside of this was that as a result of that, the instruction set became so complex that the internal circuit which was required to implement all these instructions, okay, it became so difficult to manage over time, and the instructions themselves started taking a very long time to execute. Okay, so that is why from CISC, then we came to the concept of Risc instructions, wherein it was emphasized that we should restrict ourselves to very few instructions, okay, very few addressing modes, okay. Then memory access should be limited to load and store instructions. So here you can see that, a large number of operands were allowed to be continuously uh, accessed and stored in the memory. As a result, the operations became slower. Memory was being accessed by so many, uh, instructions, so many parts of the same instruction maybe, that the overall operation started becoming very slow. So we came back to reduced instruction set computer. Okay, so you can see that the concept of Risc involves an attempt to reduce the execution time by simplifying the instruction set of the computer. Okay, the major characteristics are few instructions, few addressing modes, so everything opposite than the earlier one. Memory access limited only to load and store instructions, and all operations done within the registers of the CPU instead of relying heavily on the memory. What do we do to increase the speed? We do more and more operation in the registers. Okay, fixed length, easily decoded instruction format, single cycle instruction execution, and hardwired rather than microprogrammed control. So what is the meaning of hardwired rather than microprogrammed control? I think I have talked about this earlier. Hardwired control means, control unit means, where the control unit is directly implemented on a circuit board. Okay, so you give a power signal and everything just starts happening on its own. Microprogrammed control means microprograms such as the ones that we are writing in CPU sim now are written down for each and every instruction. So what happens is that first of all, those, even to perform a CLA kind of an instruction, okay, which can be performed directly on the AC, the computer is first required to translate the instruction into binary, okay, and then uh, actually execute the instruction. So this translation takes time. So microprogram control is good in the sense that it gives you a flexibility to vary the program. But if you don't need to vary the program, you just code the instructions once and then put them on a circuit board directly. Okay, so no need to put everything in a microprogram. That is the essence, right? So this is all that is there to that you need to look at from the CISC and Risc point of view. Okay, but even when you read your chapter, you can just go through only these sections, right?